Let's move me over here because you know you don't like those videos unless I'm in them. You know it's all about seeing this pretty mug right here. So the last time I saw you, we were talking about exponents, and today we are talking about logarithmic functions. And some of you might have worked with logarithms before, but a lot of you probably haven't, simply because we went pretty slow with school last year, and where you would have seen them maybe would have been at the end of Algebra 2. But I know I didn't get to them, and I have talked to some friends of mine who teach at other schools, and I know that a lot of them didn't actually get to logarithms either. We're going to start off with the definition and then, move on to bigger and better things. So the definition of a logarithmic function with a base of a is for x greater than 0. That's what that means. Our x has to be greater than 0. And an a not equal to 1. We're going to say that y equals log base a of x. That's how you would say this. Log base a, this sits a little bit lower, of x is the logarithmic function oh man, I'm doing this wrong. I'm reading the wrong line. If I'm fine with this, if and only if x equals a to the power of y. When I'm looking at stuff like this, when I see this y equals log base a of x, now these are different things, right? But I always like to think of it as whatever this base is raised to this power equals whatever x is. If we're writing it in function form, we would say that it's f of x equals log base a of x, but it's so much easier to work with when we change that f of x to a y. So what's a good way to show this right here? If I say have 2 equals log base 3 of 9. Say I have something that looks like that. What we're saying is if I take this 3 and I raise it to the power of 2, it will equal 9. Ultimately, I mean 3 to the power of 2. Right? 3 squared equals 9. So when we rewrite this, we could rewrite this as 3 squared equals 9. Right? The whole reason we learn it in logarithmic form is that logarithms are inverses of exponents, right? And the whole idea is that we need to start figuring out how to find things that are raised to a variable, right? We have all these exponents, but what if the exponent is the thing that's unknown? How do we solve it? Well, we use logarithms to solve it. So if I have, say, 5 to the third power equals 125, I can write that in logarithmic form as well, right? Which would be log base 3 of 125 equals 5. I could have written that as 5 equals log base 3 of 125. But ultimately, we're saying that 3, did I get that wrong? 3, 5. See what I did there? It's easy to confuse them, but it isn't difficult, right? We're saying that 5 to the third power equals 125. I'm a little sleepy today, so I hope I'm not terrible at this. It's been a while since I've done my logarithms. When we're evaluating logs, evaluating anytime you see it in math, what does it mean? It means we're plugging something in. They're going to give us a value and we have to plug it in. I am only doing the ones that you kind of need to know how to do by hand, but you can plug them into a calculator most of the time. But if I have, say, let's do problem A, f of x equals log base 2 of x, and we're saying that x equals 32, we want to know, well, if I have log base 2 of 32, what is that going to equal, right? And it'd be saying 2 raised to what power gives me 32, right? And I can tell you right off the bat that 2 to the 5th power does it, right? Now, do you always have to guess these? No, you can put it in a calculator, right?
Wait, what?
2 to what power equals 32? So 2 to the 5th power is 2 times 2 times 2 times 2 times 2.
Yeah, okay.
So
I confused. I thought it was 5.
4 times 2 is 8, times 2 is 16, times 2 is 32, right?
Mm-hmm.
And that's ultimately the question that we're asking, right? We're saying 2 to what power equals 32, right? We don't know. We have to guess. Do we have to guess? Not really. We know what it is, right? It's to the 5th power. Only simple logs like this can you do in your head, right? Once it moves into bigger and better things, you're going to need a calculator to do it. But we're just looking today at kind of the basics of logarithms, right? And to try and understand what it means when you're looking at one. So if I had, let's look at B. If I have f of x equals log base 3 of x, and we're saying that x equals 1, we're saying, well, if I have log base 3 of 1, what does that equal? We're saying 3 raised to what power equals 1? How much do you guys remember about your exponents, your rules of exponents? Anything you raise to the power of 0 equals 1.
Equals 1.
Yeah.
Yeah, funny. So 3, 3? Wait.
So it's 0.
0.
Right? Anything that you raise to the power. So if I have 3 to the power of 0, it equals 1. If I have 15 to the power of 0, it equals 1. If I have x to the power of 0, it equals 1. Anything raised to the power of 0. It's okay, Isabella. Anything raised to the power of 0 is 1. Anything raised to the power of 1 is itself. That's all I got on those like little examples of what it kind of, no, let's do one more. Let's do a C problem. If I have f of x equals log base 10 of x. Normally we don't write log base 10. What the heck's going on out there? Equals 1 over 100, right? We're saying that x equals 1 over 100. So if I plug this in, I would be saying that log base 10 of 1 over 100 means that I'm asking the question, 10 to what power equals 1 over 100? Any guesses on that? Look at how you guys see powers in terms of fractions. I just changed 10 being raised to something is giving me a fraction. Do you remember how we get a fraction out of an exponent? I know we're taking it back kind of far, probably. Getting no answers in the chat box.
I'll be honest with you. Wait, divide? Like a negative?
Yeah,
I got it?
yeah.
I got him. So
Think about this. If you think about it as if I'm raising 10 to some power and it equals 100, what will we say that power is? What is 10 to what power gives me 100? 2. Exactly. So if it was 10 to the second power, I'd get 100. If it was 10 to the negative 2 power, I would get 1/100th. Right? A negative, when we're talking about exponents, will just change the place of something within a fraction. So if I have 2 to the negative 2 power, right? Pretend that says negative 2. Well, that would be 1 over 2 squared, which is just 1/4. So anytime I have a negative power and I want to make it positive, I just have to change the place with it in the fraction. If I had 1 over 10 to the negative 2, that would just become 10 squared. It would just flip its spot within the fraction.
Out what equals 100 and then just making that a negative?
Yeah, that's exactly it. So look at what that denominator is. Whatever that base is, what would I raise that base to create that number on the bottom, right? So it's just negative. It does, right? Like I said, these aren't super complicated. It's just a matter of understanding the rules of them, which is where I'm going to start right now. We are going to talk about the properties of logarithms. We're going to change colors. Why? Because it's important to change colors sometimes. Keeps me awake. Properties of logs. This is just the first set. We'll get another set of properties of logs next week. But those are properties of operations of logarithms. Did you forget something, Giselle?
What are you looking for?
My pen.
I probably have some in that cup there if you need one.
Oh, no, it's okay. Thank you.
You're welcome. Number 1, log base A of 1 equals 0 because A to the power of 0 equals 1. Anything I raise to the power of 0 equals 1. Number 2, log base A of A equals 1. Why? Because A to the power of 1 equals A, right? We're saying that this base A raised to this power equals that. And anything raised to the power of 1 just equals itself. Here, anything raised to the power of 0 equals 1. Number 3, these are our inverse functions right here. Log base A of A to the x power equals x. And can't read my own writing. A raised to log base A of x also equals x. Why are they inverse? Because they take us back to x. Do you have to memorize these? No, but you should have them open while you're doing your assignments so you could recognize them, right? These are considered our inverse properties. Actually, those are our one-to-one. No, those are inverse. Our next one's the one-to-one. Sorry, my bad. If log base A of x equals log base A of y. Look at this. Log base A, log base A. We're saying these two things are equal, right? So if log base A of x equals log base A of y, then clearly x has to equal y, right? Because if they're equal and this is the same and this is the same, then these two things have to be equal to each other as well. Does that make some sense?
Mm-hmm.
This is our one-to-one property. So what do we do with all of this? Well, we use it when we're solving them. So I'm going to try and keep these properties up here in the picture while we look at how to use them. So if I say simplify, log base 4 of 1, right? Well, that would be this. What would it equal? Log base 4 of 1, log base A of 1 equals 0. Why? Because 4 to what power equals 0? 1. Let's try simplify. Here's a good one. Log base rad 7 of rad 7. Right? Well, look at this. This is log base A of A. It's just my A of A happens to be radical 7 and radical 7. What does log base A of A equal?
1.
1. Right? Why? Because radical 7 raised to the power of 1 equals radical 7. Does that make sense? All right, I'm glad you guys are seeing it. It's not super hard to deal with, but have your properties open when you're doing these problems. And I swear I didn't get really more difficult than this at all in the homeworks. They will all be pretty quick like this. Let's look at one more before we move on. Simplify 6 raised to the power of log base 6 of 20. So if we look up here, right? Ooh, look at that. I could just move words anywhere I want. I didn't even know I could do that. Just learned something. So here I have a log base A of x. Well, that's the same thing we have here, right? It's just our A is 6 in both of these, and our x is 20. What does it say it equals? No, it's already done. Look at the problem up here. We have a log base A of x equals x. So 6 log base 6, right? If this was 6 and this was 6.
20.
So in this case, yeah, it equals 20,
Wow.
right?
So that's done. Right?
Yeah, that's it. See, there's not a lot of work. That's why I say you should have your properties open when you guys are doing these. We're going to talk a little bit more in depth here with this one-to-one property, but we'll refer back to it. As a matter of fact, I'm going to rewrite the one-to-one property right here before we move on, just so we can see it. If log base A of x equals log base A of y, then x equals y. right? And when you look at that, that makes total sense, right? If you go, okay, well, this thing is the same and this thing is the same, which means if those are going to be equal, that x and y also have to be the same. If you think about it in those terms, it makes a lot of sense. So when we're using this one-to-one, which is what that's called, the one-to-one property, if I have a equals log base 3 of x, right? And that is equal to log base 3 of 12. If we look at this, what does that mean? It means x has to equal y. X has to equal 12, right? Because this is log base 3 and this is log base 3. These two pieces have to be equal to each other. Let's look at another one of those. Let's do one like this where we've got 2x plus 1 equals log of 3x. Notice I don't have any base on here. When we don't have a base written, it means it's log base 10, right? We call it the common log, right? Log base 10 of x or whatever is the common log, right? And we just don't write the base, right? So it's written as just log of whatever. So log of x or whatever, right? We just don't write the base when the base is 10. But it solves the same way because this is saying that this has a base of 10 and this has a base of 10. We just don't write it. So it's still 1-to-1, and we can say that 2x plus 1 equals 3x. And then we have to solve for it, right? So I can go, okay, I'm going to put all my x's on this side and all my non-x's on that side. I'm going to go, well, this is minus 1, and I get 2x equals 3x minus 1. But then I'm going to move my 3x over, and I get, I'm popular today from Scam Likely. Scam Likely keeps calling me. Minus x equals minus 1. But when we multiply or divide this, each of these by -1, we just get x equals 1, right? It just changes the sign. So we can solve that x, right, by figuring that out. But we did it using 1-to-1. We know that these two things have to be equal because everything else is equal, right? So if the whole thing's going to maintain equality, those two unknowns have to equal the same thing. Have we done anything all that difficult yet? Not really. Let's try and change it up a bit then. Let's try and make it hard. I really can't. There's not much I can do to make this difficult, right? Once you understand the concepts. I don't mean to say that the concepts are super simple. I'm just saying that once you understand them, the math part is really simple, right? If I have, let's see. I can't even read my own notes. Log base 4 of x squared minus 6 equals log base 4 of 10, right? These have the same bases. They're both log base 4. So I can say that x squared minus 6 equals 10, right? And then I just have to solve for that x squared minus 6 equals 10. So I'm going to add 6 to both sides, and I get x squared equals 16. And then I can take the square root of both sides and get x equals plus or minus 4. So that's about as difficult as it's going to get. That's probably the most you've done mathematically, right, since we started. Um, we do need to talk about the natural log and their properties. But the exciting thing is that they follow the exact same properties. Um, we talked before about e. Remember, we had that lowercase e that was equal to 2.781, blah, 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 forever and ever. It was like another kind of pi that went on forever. And we called it the natural base e. Remember? That's what we did the last time we were together, right? Well, today we're going to be talking about its inverse, which is the natural log. The natural log you have seen on your calculators, but you might not have known what it was. Right? The natural logarithm is, you've seen it on your calculator, it's defined as ln. Usually you'll see log and ln on the same button on a calculator, like one is like above it and the other is right below it. And what that is the natural log. And if we look at the function of the natural log, if we're looking at f of x equals log base e of x, we would just write that as ln of x. So that's all the natural log is. It's when that base of our logarithm is e. And instead of writing that, we write it as ln of x. Does that make some sense? So anytime we have a base that is a number, we use the log. Anytime that we have a base that is e, we use ln, right? Because that's the inverse of e. The properties are going to be the same, but we will write them out anyways. I forgot the R. So the properties of natural logs, number one is ln of 1 equals 0. Why? Because e raised to the power of 0 equals 1. Right? Just like before. We're saying anytime you see ln, that's like saying log e, log base e of 1 equals 0. So we're saying e raised to the 0 equals 1, just like with logarithms. 2, ln of e equals 1. Why? Because e to the power of 1 equals e. Anything to the power of itself equals e. It's why we say that ln is the inverse of e, which is nice because if we have e raised to something and we multiply it times ln, we're left with just the power, which you'll see as we get going. Number 3, ln of e raised to some power, ln of e of x equals x. So that's what I was just saying, right? If I multiply ln times e, say I have an e to the x and I want to know what that power is, all I have to do is multiply it times the natural log and it just equals the power, which is nice. And then the opposite of that is e raised to the ln of x equals x. That is our inverse, right? These two are our inverse functions. 4, I'll move it up a little bit. if x equals ln of y, sorry, if ln of it, oh, I don't know what I'm doing today, man. I left out letters. This is just like our last one. If ln x equals ln y, then guess what? X equals y. Does that make sense? Same as before, right? We have ln times x, ln times y. Well, the ln's are the same. If they're going to be equal, x and y also have to be the same, right? Does that make some sense? You following me there? Now, this is almost our last thing, right? I just have to give you a few examples of how to use it, but they work just like the other ones. If I have, let's say, ln of 1 over e. Well, what's that going to look like? It's going to be ln of e to the negative 1, right? We're saying, what power can I raise e to get 1 over e? Well, negative 1. B, e to the ln of 5. Well, let's look at our powers, right? I just raised e to the ln of x. Our x just happens to be 5, right? If you look over here, we're saying e to the ln of x. Well, here my x is 5. E to the ln of 5. What does it equal? It equals x. So it equals, in this case, 5. Make sense?
Mhm.
Jameson's my guide. He's like I know if you guys, I'm hoping you guys get it by
She's
whether or not
comparing you guys to me right now.
I figure, well, if Jameson can get it, the rest of you can get it.
Exactly. I agree with that statement.
ln of 1 over 3. What would that equal? Well, let's break it up. What's ln of 1? ln of 1 equals 0, right? If we look up here at our properties, so I could just say ln of 1 equals 0 over 3. What's 0 divided by 3? 0. That one makes sense? I like that one a little bit because you're kind of playing with it. You're going, okay, well, I know that ln of 1 equals 0. So I could just substitute that 0 in, and then I've got 0 over 3, and I'm not dealing with logarithms anymore. D, this will be my last sample. If I have 2 times ln of e, well, what's ln of e? ln of e is 1, right? Look at your property number 2. ln of e is 1. So this is the same as saying 2 times 1, which is just 2. Not terrible, right? Any questions about that? It's going to take a little playing with. Have your properties in front of you when you do the assignment. Play with them a little bit, okay? I know I haven't dealt with anything that's complex, really, like the math itself. The calculations are super simple. It's just a matter of understanding how the properties work. If you see something and you can substitute it in, right? I'm not hearing much in terms of questions, so I'm going to stop the video itself.